Dynamic random access memory is a type of random access memory that stores each bit of data in a separate capacitor within an integrated circuit. The capacitor can be either charged or discharged. These two states are taken to represent the two values of a bit, conventionally called 0 and 1. Since even non-conducting transistors always leak a small amount, the capacitors will slowly discharge, and the information eventually fades unless the capacitor charge is refreshed periodically. Because of this refresh requirement, it is a dynamic memory as opposed to SRAM and other static memory. The main memory in personal computers is dynamic RAM. It is the RAM in desktops, laptops and workstation computers as well as some of the RAM of video game consoles. The advantage of DRAM is its structural simplicity. Only one transistor and a capacitor are required per bit, compared to 4 or 6 transistors in SRAM. This allows DRAM to reach very high densities. Unlike flash memory, DRAM is volatile memory, since it loses its data quickly when power is removed. The transistors and capacitors used are extremely small. Billions can fit on a single memory chip. History: the cryptanalytic machine codenamed Aquarius used at Bletchley Park during World War II incorporated a hardwired dynamic memory. Paper tape was read and the characters on it were remembered in a dynamic store. The store used a large bank of capacitors, which were either charged or not, a charged capacitor representing cross and an uncharged capacitor dot. Since the charge gradually leaked away, a periodic pulse was applied to top up those still charged. In 1964 Arnold Farber and Eugene Schlig, working for IBM, created a hardwired memory cell, using a transistor gate and tunnel diode latch. They replaced the latch with 2 transistors and 2 resistors, a configuration that became known as the Farber-Schlig cell. In 1965 Benjamin Augusta and his team at IBM created a 16-bit silicon memory chip based on the Farber-Schlig cell, with 80 transistors, 64 resistors, and 4 diodes. In 1966 DRAM was invented by Dr. Robert Dennard at the IBM Thomas J. Watson Research Center. He was granted U.S. patent number 3,387,286 in 1968. Capacitors had been used for earlier memory schemes such as the drum of the Atanasoff Euroberry computer, the Williams tube and the Selectron tube. The Toshiba Toscal BC1411 electronic calculator, which was introduced in November 1966, used a form of dynamic RAM built from discrete components. In 1969 Honeywell asked Intel to make a DRAM using a 3-transistor cell that they had developed. This became the Intel 1102 in early 1970. However, the 1102 had many problems, prompting Intel to begin work on their own improved design, in secrecy to avoid conflict with Honeywell. This became the first commercially available DRAM, the Intel 1103, in October 1970, despite initial problems with low yield until the 5th revision of the masks. The 1103 was designed by Joel Karp and laid out by Pat Earhart. The masks were cut by Barbara Manis and Judy Garcia. The first DRAM with multiplexed row and column address lines was the MOST-CHEM K4096 designed by Robert Prebsting and introduced in 1973. This addressing scheme uses the same address pins to receive the low half and the high half of the address of the memory cell being referenced, switching between the two halves on alternating bus cycles. This was a radical advance, effectively halving the number of address lines required, which enabled it to fit into packages with fewer pins, a cost advantage that grew with every jump in memory size. The MK4096 proved to be a very robust design for customer applications. At the 16K density, the cost advantage increased. The MOST-CHEM K4116-16K DRAM, introduced in 1976, achieved greater than 75% worldwide DRAM market share. However, as density increased to 64K in the early 80s, MOST-CHEM was overtaken by Japanese DRAM manufacturers selling higher quality DRAMs using the same multiplexing scheme at below cost prices. See Japan-Euro-United States relations trade frictions. Most DRAM is packaged in creosol, a black epoxy resin. In 1991, Dow Chemical stopped making creosol at its chip resin plant in Freeport, Texas. On July 4, 1993, an explosion destroyed the factory that produced 60% of the world's supply of Cryosol a Sumitomo chemical factory in Miyama, Japan. Operation principle. DRAM is usually arranged in a rectangular array of charge storage cells consisting of one capacitor and transistor per data bit. The figure to the right shows a simple example with a 4x4 cell matrix. Modern DRAM matrices are many thousands of cells in height and width. The long horizontal lines connecting each row are known as word lines. Each column of cells is composed of 2-bit lines, each connected to every other storage cell in the column. They are generally known as the plus and a bit lines. Operations to read a data bit from a DRAM storage cell, the sense amplifiers are disconnected. The bit lines are pre-charged to exactly equal voltages that are in between high and low logic levels. The bit lines are physically symmetrical to keep the capacitance equal, and therefore at this time their voltages are equal. The pre-charge circuit is switched off. Because the bit lines are relatively long, they have enough capacitance to maintain the pre-charged voltage for a brief time. This is an example of dynamic logic. The desired row's word line is then driven high to connect a cell's storage capacitor to its bit line. This causes the transistor to conduct, transferring charge from the storage cell to the connected bit line or from the connected bit line to the storage cell. Since the capacitance of the bit line is typically much higher than the capacitance of the storage cell, the voltage on the bit line increases very slightly if the storage cell's capacitor is discharged and decreases very slightly if the storage cell is charged. As the other bit line holds 0.50 V, there is a small voltage difference between the two twisted bit lines. The sense amplifiers are now connected to the bit lines pairs. Positive feedback then occurs from the cross-connected inverters, thereby amplifying the small voltage difference between the odd and even row bit lines of a particular column until one bit line is fully at the lowest voltage and the other is at the maximum high voltage. Once this has happened, the row is open. All storage cells in the open row are sensed simultaneously, and the sense amplifier outputs latched. A column address then selects which latch bit to connect to the external data bus. Reads of different columns in the same row can be performed without a row opening delay because, for the open row, all data has already been sensed and latched. While reading of columns in an open row is occurring, current is flowing back up the bit lines from the output of the sense amplifiers and recharging the storage cells. This reinforces the charge in the storage cell by increasing the voltage in the storage capacitor if it was charged to begin with, or by keeping it discharged if it was empty. Note that due to the length of the bit lines there is a fairly long propagation delay for the charge to be transferred back to the cell's capacitor. This takes significant time past the end of sense amplification, and thus overlaps with one or more column reads. When done with reading all the columns in the current open row, the word line is switched off to disconnect the storage cell capacitors from the bit lines. The sense amplifier is switched off, and the bit lines are pre-charged again. To write to memory, to store data, a row is opened and a given column's sense amplifier is temporarily forced to the desired high or low voltage state, thus causing the bit line to charge or discharge the cell storage capacitor to the desired value. Due to the sense amplifier's positive feedback configuration, it will hold a bit line at stable voltage even after the forcing voltage is removed. During a write to a particular cell, all the columns in a row are sensed simultaneously just as during reading, so although only a single column's storage cell capacitor charge is changed, the entire row is refreshed, as illustrated in the figure to the right. Refresh rate. Typically, manufacturers specify that each row must have its storage cell capacitors refreshed every 64 ms or less, as defined by the JEDEC standard. Refresh logic is provided in a DRAM controller which automates the periodic refresh. Stated differently, no software or other hardware has to perform it. This makes the controller's logic circuit more complicated, but this drawback is outweighed by the fact that DRAM is much cheaper per storage cell, and because each storage cell is very simple, DRAM has much greater capacity per unit of surface than SRAM. Some systems refresh every row in a burst of activity involving all rows every 64 ms. Other systems refresh one row at a time staggered throughout the 64 milliseconds interval. For example, A system with 213 A equals A8192 rows would require a staggered refresh rate of 1 row every 7.8 A microsecond, which is 64 ms divided by 8192 rows. A few real-time systems refresh a portion of memory at a time determined by an external timer function that governs the operation of the rest of the system, such as the vertical blanking interval that occurs every 10–20 ms in video equipment. All methods require some sort of counter to keep track of which row is the next to be refreshed. Most DRAM chips include that counter. Older types require external refresh logic to hold the counter. Under some conditions, most of the data in DRAM can be recovered even if the DRAM has not been refreshed for several minutes. Memory timing. Many parameters are required to fully describe the timing of DRAM operation. Here are some examples for two timing grades of asynchronous DRAM, from a data sheet published in 1998. Thus, the generally quoted number is the /AS access time. This is the time to read a random bit from a pre-charged DRAM array. The time to read additional bits from an open page is much less. When such a RAM is accessed by clocked logic, the times are generally rounded up to the nearest clock cycle. For example, when accessed by a 100 MHz state machine, the 50 ANS DRAM can perform the first read in 5 clock cycles, and additional reads within the same page every 2 clock cycles. This was generally described as 5 €2 or 2 euros or 2 euros timing, as bursts of 4 reads within a page were common. When describing synchronous memory, timing is described by clock cycle count separated by hyphens. These numbers represent TCLA Euro TRCDA Euro TRPA Euro TRAS in multiples of the DRAM clock cycle time. Note that this is half of the data transfer rate when double data rate signaling is used. JEDEC standard PC3200 timing is 3 or 4 euros or 4 euros or 8 euros with a 200 MHz clock, while premium-priced high-performance PC3200 DDR DRAM DIMM might be operated at 2 or 2 euros or 2 euros or 5 euros timing. Minimum random access time has improved from TRACN equals A50 ANS to TRCD plus TCL equals 22.5 ANS, and even the premium 20 ANS variety is only 2.5 times better compared to the typical case. CAS latency has improved even less, from TCAC equals 13 ANS to 10 ANS. However, the DDR3 memory does achieve 32 times higher bandwidth. Due to internal pipelining and wide data paths, it can output 2 words every 1.25 ANS, while the EDO DRAM can output 1 word per TPCA equals A20 ANS. Timing abbreviations, error detection and correction. Electrical or magnetic interference inside a computer system can cause a single bit of DRAM to spontaneously flip to the opposite state. The majority of one-off errors in DRAM chips occur as a result of background radiation, chiefly neutrons from cosmic ray secondaries, which may change the contents of one or more memory cells or interfere with the circuitry used to read-write them. Recent studies give widely varying error rates for single event upsets with over 7 orders of magnitude difference, ranging from roughly 1 bit error, per hour, per gigabyte of memory to 1 bit error, per century, per gigabyte of memory. This problem can be mitigated by using redundant memory bits and memory controllers that exploit these bits, usually implemented within DRAM modules. These extra bits are used to record parity and to enable missing data to be reconstructed by error-correcting code. Parity allows the detection of all single-bit errors. The most common error-correcting code, a sectored Hamming code, allows a single-bit error to be corrected and, in the usual configuration, with an extra parity bit, double-bit errors to be detected. An ECC-capable memory controller as used in many modern PCs can typically detect and correct errors of a single bit per 64-bit word, and detect errors of 2 bits per 64-bit word. Some systems also scrub the errors, by writing the corrected version back to memory. The BIOS in some computers, and operating systems such as Linux, allow counting of detected and corrected memory errors. This allows identification and replacement of failing memory modules. Recent studies give widely varying error rates with over 7 orders of magnitude difference, ranging from 10 a 10 a 10 a 17 error BTH, roughly 1 bit error, per hour, per gigabyte of memory to 1 bit error, per century, per gigabyte of memory. The Schroeder et al. 2009 study reported a 32% chance that a given computer in their study would suffer from at least one correctable error per year, and provided evidence that most such errors are intermittent hard rather than soft errors. A 2010 study at the University of Rochester also gave evidence that a substantial fraction of memory errors are intermittent hard errors. Large-scale studies on non-SRAM in PCs and laptops suggest that undetected memory errors account for a substantial number of system failures. The study reported a 1 in 1700 chance per 1.5% of memory tested that a computer would have a memory error per 8 months. Packaging. For economic reasons, the large memories found in personal computers, workstations, and non-handheld game consoles normally consist of dynamic RAM. Other parts of the computer, such as cache memories and data buffers in hard disks, normally use static RAM. General DRAM formats. Dynamic random access memory is produced as integrated circuits bonded and mounted into plastic packages with metal pins for connection to control signals and buses. In early use, individual DRAM ICs were usually either installed directly to the motherboard or on ISA expansion cards. Later they were assembled into multi-chip plug-in modules. Some standard module types are DRAM chip, dual inline package. DRAM modules, single inline pin package, single inline memory module, dual inline memory module, rambus inline memory module, technically DIMMs but called RIMMs due to their proprietary slot. Small outline DIMM, about half the size of regular DIMMs, are mostly used in notebooks, small footprint PCs, upgradable office printers and networking hardware like routers. Comes in versions with 72-pin, 144-pin used for SDRAM, 200-pin used for DDR SDRAM and DDR2 SDRAM, 204-pin used for DDR3 SDRAM. Small outliner IMM. Smaller version of the RIMM, used in laptops. Technically SODIMMs but called SORIMMs due to their proprietary slot. Stacked versus non-stacked RAM modules. Stacked RAM modules contain 2 or more RAM chips stacked on top of each other. This allows large modules to be manufactured using cheaper low-density wafers. Stacked chip modules draw more power, and tend to run hotter than non-stacked modules. Stacked modules can be built using the older TSOP or the newer BGA-style IC chips. Common DRAM modules. Common DRAM packages as illustrated to the right, from top to bottom, DIP 16-pin, SIPP 30-pin, SIMM 30-pin, SIMM 72-pin but FPRAM is not uncommon, DIMM 168-pin, DIMM 184-pin, RIMM 184-pin not pictured, DIMM 240-pin not pictured. Memory size of a DRAM module. The exact number of bytes in a DRAM module is always an integral power of 2. A 512 MB's DRAM DIMM actually contains 512 MB equals 512 220 bytes equals 229 bytes equals 536,870,912 bytes exactly, and might be made of 8 or 9 SDRAM chips, each containing exactly 512 MB of storage, and each one contributing 8 bits to the DIMM 64 or 72 Euro bit width. For comparison, a 2 GB SDRAM module contains 2 GB equals 2 230 bytes equals 231 bytes equals 2,147,483,648 bytes of memory, exactly. The module usually has 8 SDRAM chips of 256 MB each. Versions. While the fundamental DRAM solid array has maintained the same basic structure for many years, there have been many different interfaces for communicating with DRAM chips. When one speaks about DRAM types, one is generally referring to the interface that is used. Asynchronous DRAM. An asynchronous DRAM chip has power connections, some number of address inputs, and a few bidirectional data lines. There are 4 active low control signals, /RAS, the row address strobe. The address inputs are captured on the falling edge of /RAS, and select a row to open. The row is held open as long as /RAS is low. /CAS, the column address strobe. The address inputs are captured on the falling edge of /CAS, and select a column from the currently open row to read or write. /WE, write enable. The signal determines whether a given falling edge of /CAS is a read or write. If low, the data inputs are also captured on the falling edge of /CAS. /OE, outputs enable. This is an additional signal that controls output to the data I/O pins. The data pins are driven by the DRAM chip if /RAS and /CAS are low, /WE is high, and /OE is low. In many applications, /OE can be permanently connected low, but it can be useful when connecting multiple memory chips in parallel. This interface provides direct control of internal timing. When /RAS is driven low, a /CAS cycle must not be attempted until the sense amplifiers have sensed the memory state, and /RAS must not be returned high until the storage cells have been refreshed. When /RAS is driven high, it must be held high long enough for pre-charging to complete. Although the RAM is asynchronous, the signals are typically generated by a clocked memory controller, which limits their timing to multiples of the controller's clock cycle. RAS-only refresh, classic asynchronous DRAM is refreshed by opening each row in turn. The refresh cycles are distributed across the entire refresh interval in such a way that all rows are refreshed within the required interval. To refresh one row of the memory array using /RAS-only refresh, the following steps must occur. The row address of the row to be refreshed must be applied at the address input pins. /RAS must switch from high to low. /CAS must remain high. At the end of the required amount of time, /RAS must return high. This can be done by supplying a row address and pulsing /RAS low. It is not necessary to perform any /CAS cycles. An external counter is needed to iterate over the row addresses in turn. CAS before RAS refresh. For convenience, the counter was quickly incorporated into RAM chips themselves. If the /CAS line is driven low before /RAS, then the DRAM ignores the address inputs and uses an internal counter to select the row to open. This is known as RAS refresh. This became the standard form of refresh for asynchronous DRAM, and is the only form generally used with SDRAM, hidden refresh. Given support of CAS before RAS refresh, it is possible to desert /RAS while holding /CAS low to maintain data output. If /RAS is then asserted again, this performs a CBA refresh cycle while the DRAM outputs remain valid. Because data outputs is not interrupted, this is known as hidden refresh. Video DRAM. VRAM is a dual-ported variant of DRAM that was once commonly used to store the frame buffer and some graphics adapters. Window DRAM. WRAM is a variant of VRAM that was once used in graphics adapters such as the Matrox Millennium and ATI 3D Rage Pro. WRAM was designed to perform better and cost less than VRAM. WRAM offered up to 25% greater bandwidth than VRAM and accelerated commonly used graphical operations such as text drawing and block fills. Fast Page Mode DRAM. Fast Page Mode DRAM is also called FPM DRAM, FPRAM, Page Mode DRAM, Fast Page Mode Memory, or Page Mode Memory. In page mode, a row of the DRAM can be kept open by holding /RAS low while performing multiple reads or writes with separate pulses of /CAS so that successive reads or writes within the row do not suffer the delay of pre-charge and accessing the row. This increases the performance of the system when reading or writing bursts of data. Static column is a variant of page mode in which the column address does not need to be stored in, but rather, the address inputs may be changed with /CAS held low, and the data output will be updated accordingly a few nanoseconds later. Nibble mode is another variant in which 4 sequential locations within the row can be accessed with 4 consecutive pulses of /CAS. The difference from normal page mode is that the address inputs are not used for the second through fourth /CAS edges. They are generated internally starting with the address supplied for the first /CAS edge. Extended Data Out DRAM. EDO DRAM, sometimes referred to as Hyperpage Mode Enabled DRAM, is similar to Fast Page Mode DRAM with the additional feature that a new access cycle can be started while keeping the data output to the previous cycle active. This allows a certain amount of overlap in operation, allowing somewhat improved performance. It was 5% faster than FPM DRAM, which it began to replace in 1995, when Intel introduced the 430FX chipset that supported EDO DRAM. To be precise, EDO DRAM begins data output on the falling edge of /CAS, but does not stop the output when /CAS rises again. It holds the output valid until either /RAS is deserted, or a new /CAS falling edge selects a different column address. Single-cycle EDO has the ability to carry out a complete memory transaction in one clock cycle. Otherwise, each sequential RAM access within the same page takes 2 clock cycles instead of 3, once the page has been selected. EDO's performance and capabilities allowed it to somewhat replace the then slow L2 caches of PCs. It created an opportunity to reduce the immense performance loss associated with a lack of L2 cache, while making systems cheaper to build. This was also good for notebooks due to difficulties with their limited form factor, and battery life limitations. An EDO system with L2 cache was tangibly faster than the older FPM L2 combination. Single-cycle EDO DRAM became very popular on video cards towards the end of the 1990s. It was very low cost, yet nearly as efficient for performance as the far more costly VRAM. Much equipment taking 72-pin SIMMs could use either FPM or EDO. Problems were possible, particularly when mixing FPM and EDO. Early Hewlett-Packard printers had FPM RAM built in. Some, but not all, models worked if additional EDO SIMMs were added. Burst EDO DRAM, an evolution of EDO DRAM, burst EDO DRAM, could process 4 memory addresses in one burst, for a maximum of 5 or €1, saving an additional 3 clocks over optimally designed EDO memory. It was done by adding an address counter on the chip to keep track of the next address. The EDO also added a pipelined stage allowing page access cycle to be divided into 2 components. During a memory read operation, the first component accessed the data from the memory array to the output stage. The second component drove the data bus from this latch at the appropriate logic level. Since the data is already in the output buffer, quicker access time is achieved than with traditional EDO. Although BEDO DRAM showed additional optimization over EDO, by the time it was available the market had made a significant investment towards synchronous DRAM, or SRAM, too. Even though BEDO RAM was superior to SRAM in some ways, the latter technology quickly displaced BEDO. Multibank DRAM. Multibank DRAM applies the interleaving technique for main memory to second-level cache memory to provide a cheaper and faster alternative to SRAM. The chip splits its memory capacity into small blocks of 256 kilobytes and allows operations to 2 different banks in a single clock cycle. This memory was primarily used in graphic cards with Tsim Labs ET6X00 chipsets, and was made by MOSIS. Boards based upon this chipset often use the unusual RAM-sized configuration of 2.25 megabytes, owing to MDRAM's ability to be implemented in various sizes more easily. The size of 2.25 megabytes allowed 24-bit color at a resolution of 1024A, 768. A very popular display setting in the card's time. Synchronous graphics RAM. SGRAM is a specialized form of SDRAM for graphics adapters. It adds functions such as bit masking and block write. Unlike VRAM and WRAM, SGRAM is single-ported. However, it can opening 2 memory pages at once, which simulates the dual-port nature of other video RAM technologies. GDDR, or Graphics Double Data Rate Memory, refers to memory specifically designed for use on graphics cards. GDDR is distinct from the more widely known DDR-SDRAM types such as DDR3, although they share some technologies, including double data rate design. Currently, the following generations of GDDR exist, with the higher number indicating the more recent specifications: GDDR2, GDDR3, GDDR4, GDDR5. GDDR5, or Graphics Double Data Rate version 5, SRAM is a type of memory designed for use in graphics cards and other computer applications requiring high bandwidth. Like its predecessor, GDDR4, GDDR5 is based on DDR3 SRAM, which has double the data lines compared to DDR2 SRAM, but GDDR5 also has 8-bit wide prefetch buffers similar to GDDR4. GDDR5 SRAM conforms to the standards which were set out in the GDDR5 specification by the JEDEC. It uses an 8N prefetch architecture and DDR interface to achieve high-performance operation and can be configured to operate in A32 mode or A16 mode, which is detected during device initialization. The GDDR5 interface transfers two 32-bit wide data words per write clock cycle to from the I/O pins. Corresponding to the 8N prefetch, a single write or read access consists of a 256-bit Y2CK clock cycle data transfer at the internal memory core and 8 corresponding 32-bit wide 1/2 WCK clock cycle data transfers at the I/O pins. GDDR5 operates with two different clock types: a differential command clock as a reference for address and command inputs, and a forwarded differential write clock as a reference for data reads and writes, but runs at twice the CK frequency. Being more precise, the GDDR5 SRAM uses a total of 3 clocks, 2 write clocks associated with 2 bytes and a single command clock. Taking a GDDR5 with 5-bit S data rate per pin as an example, the CK clock runs with 1.25 GHz and both WCK clocks are 2.5 GHz. The CREAK and WCKs are phase-aligned during the initialization and training sequence. This alignment allows read and write access with minimum latency. A single 32-bit GDDR5 chip has about 67 signal pins and the rest are power and grounds in the 170 BGA package. Synchronous dynamic RAM. SRAM significantly revises the asynchronous memory interface, adding a clock line. All other signals are received on the rising edge of the clock. The /RAS and /CAS inputs no longer act as strobes, but are instead, along with /WE, part of a 3-bit command. The /OE lines function is extended to a per byte DQM signal, which controls data input in addition to data output. This allows DRAM chips to be wider than 8 bits while still supporting byte granularity writes. Many timing parameters remain under the control of the DRAM controller. For example, a minimum time must elapse between a row being activated and a read or write command. One important parameter must be programmed into the SRAM chip itself, namely the CAS latency. This is the number of clock cycles allowed for internal operations between a read command and the first data word appearing on the data bus. The load mode register command is used to transfer this value to the SRAM chip. Other configurable parameters include the length of read and write bursts, that is the number of words transferred per read or write command. The most significant change, and the primary reason that SRAM has supplanted asynchronous RAM, is the support for multiple internal banks inside the DRAM chip. Using a few bits of bank address, which accompany each command, a second bank can be activated and begin reading data while a read from the first bank is in progress. By alternating banks, an SRAM device can keep the data bus continuously busy, in a way that asynchronous DRAM cannot. Single data rate. Single data rate SRAM is a synchronous form of DRAM. Double data rate. Double data rate SRAM was a later development of SRAM, used in PC memory beginning in 2000. Subsequent versions are numbered sequentially. DDR SRAM internally performs double width accesses at the clock rate, and uses a double data rate interface to transfer 1/2 on each clock edge. DDR2 and DDR3 increased this factor to 4A and 8A, respectively, delivering 4-word and 8-word bursts over 2 and 4 clock cycles, respectively. The internal access rate is mostly unchanged, but each access transfers more data. Direct Rambus DRAM. Direct Rambus DRAM was developed by Rambus. Pseudostatic RAM, PSRAM or PSDRAM is dynamic RAM with built-in refresh and address control circuitry to make it behave similarly to static RAM. It combines the high density of DRAM with the ease of use of true SRAM. PSRAM is used in the Apple iPhone and other embedded systems such as XFLAR platform. Some DRAM components have a self-refresh mode. While this involves much of the same logic that is needed for pseudostatic operation, this mode is often equivalent to a standby mode. It is provided primarily to allow a system to suspend operation of its DRAM controller to save power without losing data stored in DRAM, rather not to allow operation without a separate DRAM controller as is the case with PSRAM. An embedded variant of PSRAM is sold by MOSIS under the name 1T SRAM. It is technically DRAM, but behaves much like SRAM. It is used in Nintendo GameCube and Wii consoles. Reduced latency DRAM. Reduced latency DRAM is a high-performance double data rate SDRAM that combines fast, random access with high bandwidth, mainly intended for networking and caching applications. 1 trillion DRAM. Unlike all of the other variants described in this section of this article, 1 trillion DRAM is a different way of constructing the basic DRAM bit cell. 1 trillion DRAM is a capacitorless bit cell design that stores data in the parasitic body capacitor that is an inherent part of silicon on insulator transistors. Considered a nuisance in logic design, this floating body effect can be used for data storage. Although refresh is still required, reads are non-destructive. The stored charge causes a detectable shift in the threshold voltage of the transistor. There are several types of 1 trillion DRAMs, the commercialized SRAM from Innovative Silicon, the TTRAM from Renesas and the ARAM from the UGRC-NRS consortium. The classic 1 transistor 1 capacitor DRAM cell is also sometimes referred to as 1 trillion DRAM, particularly in comparison to 3T and 4 trillion DRAM which it replaced in the 1970s. Security. Although dynamic memory is only specified and guaranteed to retain its contents when supplied with power and refreshed every short period of time, the memory cell capacitors often retain their values for significantly longer, particularly at low temperatures. Under some conditions most of the data in DRAM can be recovered even if it has not been refreshed for several minutes. This property can be used to circumvent security and recover data stored in memory and assumed to be destroyed at power down by quickly rebooting the computer and dumping the contents of the RAM, or by cooling the chips and transferring them to a different computer. Such an attack was demonstrated to circumvent popular disk encryption systems, such as the open-source TrueCrypt, Microsoft's BitLocker drive encryption, and Apple's File Vault. This type of attack against a computer is often called a cold boot attack. See also, DRAM price fixing, DIMM, flash memory, regenerative capacitor memory, static random access memory, list of device bandwidths, memory geometry, references. External links, modern DRAM memory systems, performance analysis and a high-performance, power-constrained DRAM scheduling algorithm. A PhD dissertation by David Tawai Wang, has very well-written and detailed discussion on how DRAM works. DRAM density and speed trends has some interesting historical trend charts of DRAM density and speed from 1980. Back to Basics. Memory, Part 3, Benefits of Chip Kill Correct ECC for PC Server Main Memory. A 1997 discussion of SDRAM reliability. Some interesting information on soft errors from cosmic rays, especially with respect to error-correcting code schemes. A teaser on Semiconductor Soft Error White Paper 1994 Literature Review of Memory Error Rate Measurements. Soft Errors Impact on System Reliability. Ritis Masterprom and Edwin C. Wee, Cypress Semiconductor, 2004, Scaling and Technology Issues for Soft Error Rates. A. Johnstone. A 4th Annual Research Conference on Reliability. Stanford University, October 2000, Challenges and future directions for the scaling of dynamic random access memory. J. A. Mandelman, R. H. Dennard, G. B. Bronner, J. K. DeBross, R. Divakaruni, Y. Lee, and C. J. Radines, IBM 2002, Ars Technica, RAM Guide, Versatile DRAM Interface for the 6502 CPU, David Tawai Wang. Modern DRAM Memory Systems, Performance Analysis and a High-Performance, Power-Constrained DRAM Scheduling Algorithm. Ph.D. Thesis, University of Maryland, College Park. Retrieved March 10, 2007. A detailed description of current DRAM technology. The Toshiba Toscal BC1411 desktop calculator. An early electronic calculator that uses a form of dynamic RAM built from discrete components. Mitsubishi's 3D RAM and cached RAM incorporate high-performance, onboard SRAM cache, multi-port cached RAM. MP RAM, How to install DRAM installation guide for desktop and laptop computers. 3. DRAM errors in the wild, a large-scale field study. What every programmer should know about memory by Ulrich Drepper, continued with, CPU caches, virtual memory, NUMA systems, what programmers can do, cache optimization, what programmers can do, multi-threaded optimizations, memory performance tools, future technologies.